Hello, everyone. So today we have a very distinguished speaker, Professor Mehran Kardar from MIT. So his research covers a wide variety of topics spanning statistical physics, soft matter, biophysics, and fluctuation-induced phenomena. So he is well known for introducing a particular nonlinear partial differential equation in the context of growth models, surface growth models. So this famous equation is now known as the Kardar-Parisi-Zhang equation, which defines many interacting problem, and thus it actually forms a university class, and it's still a subject of very hot subject of research. Okay. So apart from being a brilliant researcher, he's also a very excellent teacher. I mean, some of his courses are available on the MIT Open Courseware platform, and I'd urge the student to actually go and look at these courses. So he has authored 2 excellent statistical physics books, and I mean, many of us use these books for teaching or. So he is a fellow of American Physical Society, American Academy of Arts and Sciences, and National Academy of Sciences. So apart from this, he has received numerous other awards and honors, so that I'll not list here. So finally, I'd like to actually thank him for this following reason. So although we had actually offered him a flexible time, because I mean, as we do with overseas speakers these days, and most speakers actually take this offer, and then usually our talks are in the evening. But Professor Kardar insisted that he will speak on the regular time, and so he is basically now speaking in the early morning, 5:30 a.m. from Boston. So I'm very thankful to you for this. Yeah. And so today he's going to talk about competitive growth on a rugged front. And yeah, over to you, Professor Kardar. Yeah.
Thank you very much, Sanjeev, for a very kind introduction and also the invitation to speak. So I will be talking about a topic of range expansions in biology, which is when new species grow into new territory, and then the important events are taking place at the front of this expanding population. And maybe a good way to introduce some of these complications is by a bacterial example, which was an experiment that was done by David Nelson, Sharad Ramanathan, and others in 2007. The picture that you see on A is when they put a drop of bacteria in the center of a dish, and then the bacteria started growing, and what you're seeing is the growth pattern. And the origin of the colors is as follows, that the initial drop contained a mixture of 2 versions of these E. coli bacteria that for all intents and purposes were identical, except that to them was added a particular protein that would cause the bacteria to either fluoresce in red or in green. The initial drop contained the mixture, and because of that, the color appears as orange. But as this bacteria grow into the dish, we can see that there is this appearance of segments that are either green or red. And the origin of this separation of colors is that once in some region, by chance, the green, for example, has established itself, all of the offspring of green will continue to be green, and so this green portion will continue to expand. So there is some reduction in diversity as this growth occurs that one can also see in different geometries. For example, in the bottom picture in C, what they did is rather than start the colony from a circular drop, they dipped the edge of a knife, if you like, into the mixture of bacteria and then put it on the plate. And then the growth started to proceed from a flat front. And again, similar type of patterns can be seen here. For purposes of writing equations and analyzing this starting point of a straight edge is somewhat more convenient, and a model that can sort of justify why these different colors appear in sectors, which they also introduced, is called the stepping stone model. So imagine that the initial point of the straight edge, you have bacteria of different colors that are introduced. And for the purposes of this simulation, let's have even more colors than just the two that they had in the experiment. But ultimately, as time goes on, the number of colors gets reduced. And in this case, after 5 or 6 steps, you only have red or blue. The growth rule for this model is very simple. Basically, you look at the front and you pick one of the colors that you have on the front, say at time t, and have them reproduce and go at the next level. And it could be that some of the bacteria or some of the model bacteria in this case do not reproduce and others do reproduce. And because of that, there is some colors that could disappear. And what you see here is a collection of many of these, and eventually there is some reduction in the number of colors. Now, the thing to sort of think about this from the perspective of statistical physics is that if we look at the boundary that is separating two of these sectors, say red and blue, clearly the point at the front can be selected randomly from the left or to the right and will execute some kind of a random walk. So the expectation is that if this model is an accurate reflection of the reality, the fluctuations of the boundary between two sectors as you go further in time should have a scaling that is characteristic of a random walk with an exponent of 1/2. Now, when they actually do look at this experiment and characterize the extent of these transverse fluctuations as you proceed further in time, what they find is that the scaling is larger than what would be expected on the basis of diffusion. Delta x squared, rather than growing as t, grows with an exponent that is closer to 4/3. And so what they proposed is just a very simple modification of the previous model. And the modification is that the previous model, the growth was one layer and then another layer, so that the front was always remaining flat, whereas a more realistic situation is to allow any of the bacteria at the front to reproduce. And if you don't do that synchronously, one layer at a time, then the front becomes rough. And so this is a picture that would emerge from this version of the stepping stone model, in which the growth is not one layer at a time, it becomes rough. And then the roughness of this front is also reflected in the sectors that are separating the different regions. And in this case, the fluctuations, just by making this simple change from synchronous to asynchronous growth at the front, changes in exponent from 1/2 to 2/3, which is characteristic of roughness of growing surfaces. And the explanation for that, which I will then use in other things that I will be describing. So this is kind of a classic known result, but I will emphasize this, is that one may imagine that the front is growing with a uniform velocity. Let's call it V0. But if it is no longer a flat surface, the velocity at a particular point on the surface can depend on the curvature of the surface. And this is a term that would tend to make it smooth, but it can also depend on other characteristics of the surface. For example, its slope. And so the sloped surface may be growing at a different velocity, and that's captured here. And of course, because of the randomness in the reproduction or other events, one can add also noise to this process that is the origin of the roughness. And what is known for some time is that depending on whether the growth velocity depends or does not depend on the slope, that is either lambda equals to 0 or lambda not equal to 0, the scaling of the fluctuations of space and time characterized by an exponent that was previously either 1/2 or 2/3 gets modified such that if there is no dependence on slope, the slope is, the exponent is diffusive. And if it is, there is dependence on slope, it becomes super diffusive. Okay, so what are the consequences of that for the biological systems? So one of the things that I had in the previous picture, but I did not describe so far, were these black lines. And so what are these black lines? Let us pick two bacteria that are on the front and ask about their ancestry. That is, for a particular bacterium, if we go back to the previous picture here, let's say this bacterium, its parent was this one, and then the parent of that may have been another one here. So we can construct a black line, like any of these black lines, that traces the ancestry of the bacterium at the front. And these ancestral traces naturally collide with each other when we reach their most recent common ancestor. And so this pattern of lines coalescing is a characterization of the family tree, if you like, of the bacteria that are living on the front. Now, that's one perspective on this growing colony. And the other perspective that I already mentioned is that there are these boundaries between the sectors. And both sector boundaries and the lines tracing the ancestry satisfy these kinds of fluctuations that I mentioned before, which we may be interested in quantifying in the following sense. As time proceeds, the number of colors certainly gets reduced. And so if you like, there are various extinction events in which one particular color disappears. And so we want to know how these extinctions take place. And the question that we can ask is, let's say if we have a domain that initially spans a length of size delta x, what is the chance that after some time tau it has disappeared? Or alternatively, we can ask the question, if I have two bacteria at the front that are separated by a distance delta x, how far back in time do I have to go in order to find their nearest common ancestor? So both of these questions from the perspective of statistical physics are descriptor of the probability that two of these fluctuating lines coalesce for the first time after a certain amount of time. Now, if the problem was described by random walks, this is a very classical problem, which is essentially the first collision of random walks that has been studied for a long time. And one can find the answer exactly by going through the method of images. And the answer depends on the separation delta x as well as time through a behavior that is governed by the scaling of delta x squared with tau. And it has certain interesting limits, such as when times are much larger than average, or when times are much smaller than average. In one case, you have a power law dependence, and in the other case, you have you are dominated by the exponential Gaussian form. Now, the corresponding results for the case when these walkers are not random walks and not just versions of the random walk when we give them some kernel to make them super diffusive, but random walks, super diffusive random walks that are created through this process was not known, and I guess still is not known analytically. So what we did was we went and did simulations, and not surprisingly, the results of the simulations can be scaled by this combination that is related to delta x and tau raised to the 2 terms as opposed to 1/2 exponent. But the precise dependencies of this function that we don't know in general in the limit of long times or short times, again, we could not even those limits determine analytically, but numerically they seem to have rather simple forms. And so a challenge could potentially be to try to figure out these forms exactly. So at this point, we only have numerical results. Now, these forms are something that are of interest to a statistical physicist, but if you are a biologist, you don't really care about all of these scaling forms. So we can summarize the answer as follows, that because of this super diffusive meandering of these lines, two things that are biologically important occur. One of them is that the common ancestors are more recent and fewer in number, because these lines are more likely to cross each other and coalesce because they are fluctuating more. And secondly, that genetic diversity in this system where the front becomes rough disappears much more rapidly than the flat front growth. So these are kind of simple ways of capturing the result of the super diffusive fluctuations of sectors and ancestral lines in a language that is appropriate to biology. Now, I'd like to sort of focus more on this extinction of species and disappearance of diversity as time goes on, but somewhat in a more general setting. Because in the previous case that I was describing, the two species that were introduced originally were, for all intents and purposes, except the color that they had been endowed with, identical in the way that they were growing. But typically, when you have different species at the same time, one of them may have an advantage over the other. And because of that advantage, the other species, the less fit species, would disappear more rapidly. And to parameterize that, let's imagine that we have two species that I call A and B, whose numbers changes as a function of time by different growth parameters that I've called GA and GB. So if there was nothing else to go on, each species would grow exponentially, but one of them potentially at a different rate from the other. One could also allow mutations in which the B species mutates into A, or the A species mutates into B. And so this would be the equations that, in the absence of any competition for resources, would describe the different exponential growths of these two species. Now, if we want to insist that the population on average does not change, maybe the sum of the two growth factors we can set to 0. And then we can look at the fraction of, say, A over the total population. And the equation that governs the fraction is something that has potentially absorbing states, which correspond to one species going extinct. But before going to that, let us add two more features to this equation. One of them is that rather than having them appear as a mixed bag, let's put the different species in space. And in that case, one would have diffusion of the two species and spread in space. And secondly, let us add noise. And one of the interesting things, if we were to discretize these set of equations rather than having a continuous NA, but NA that is a discrete number, and go through the master equation formalism in the continuum limit, the noise will be something that appears with a variance or an amplitude that is proportional to the product of the fractions f and 1 minus f, the fraction of one times the fraction of the other. Now, as I kind of started to say at the beginning, if one of the mutation factors is 0, so that in that case, either f equals to 0 or f equals to 1 would be an absorbing state. So if one of the species cannot be created from the other by mutation, then that species by fluctuations will disappear over time. And this extinction event is then described by a version of this equation, which is very much similar to the, time-dependent Landau-Ginzburg equation. There is a fraction f that could potentially grow with a rate that is a difference between the different growth factors. There is a saturation, so this kind of looks like Fisher equation when we add diffusion. And the only difference from standard type of Landau-Ginzburg equations is that the strength of the noise is proportional to the square root of this fraction or order parameter. And what this means is that f equals to 0 corresponds to an absorbing state. So if you are at f equals to 0, you will stay at f equals to 0 forever. And that extinction event, if one looks at this equation and analyze it, belongs to the so-called directed percolation universality class. And I can make a model that casts this type of behavior in terms of growth of bacterial films as follows. Let's imagine again that I have a layer by layer growth of bacteria that are of two colors, these bricks that are either blue or gray. And if I allow for the possibility of gray mutating into blue, but not vice versa, eventually as a function of time, everything would become gray and the blue would go extinct. And if I trace the fluctuations of these patterns, I will generate these kinds of interesting figures. Eventually it will become gray, but there are some interesting fluctuations in the middle. But as we have seen, for a realistic bacterial growth requiring this synchronous layer by layer growth is not necessarily correct. And if we allow a version of this same model in which the front becomes rough, then the shape of the domains and the fluctuations that one inherits from the growing front are different. So how can we modify this directed percolation universality class that describes the extinction of this model where the growth is layer by layer to also be able to describe this kind of growth which has a rough surface? And the idea to do that is that the roughness of the surface again introduce another slow parameter, a slow field in the problem, which is the fluctuations in height of the interface. And maybe what we should do is to modify our directed percolation equation for the growth of the different competing species to also describe the height of this front. So if you recall, when we were thinking about just the front that was growing, I said that the vertical growth velocity could depend on curvature as well as slope. But why not the growth velocities of the species in the plane as opposed to normal to the plane? Why shouldn't they depend on the curvature and the slope of the front? it is allowed by symmetry for a rough surface. And if I allow the way in which the species move in the parallel to the front as opposed to perpendicular to the front to also depend on curvature and the slope of the front, then I will have a variation of the equation that I had written before that was in the directed percolation universality class, where there are couplings between the fraction of the species that is close to going extinct and the slope and the curvature of the front. So this is one aspect of modifying the equation. The velocity of the front will itself be modified because if the two species are not identical, there is no reason why the vertical growth velocity at the blue and the gray region should be the same. There could be a difference between them that could be captured by a term that in turn couples the fraction to the growth of the height. So this way we can couple the directed percolation equation for the fraction f and the height equation for the rough surface together. And it is easy to show if one does power counting that the leading terms that one gets in a gradient expansion are the four terms that I have added here. And I will describe to you later on what the actual meaning of these four terms is and how they modify the surface. Now, from the perspective of statistical physics, then you can ask, well, the old equation described the directed percolation universality class for extinction. How does the addition of these new terms modify this universality class? These terms are, from the perspective of power counting, relevant below 4 dimensions. And with Jordan Horowitz, we try to do a renormalization group. And beyond showing that all 4 of them are relevant, we couldn't really do much. We could not find a fixed point that described the new universality class. So one needs to go and do computer simulations to describe what the nature of the exponents are for this new universality class, such as some simulations that Erwin Frey has done several years ago. But I will not continue with the universality class, but rather try to describe the effect of these terms that I have introduced here in shapes, morphologies, and pictures of growing fronts that we can see. So I kind of introduced these new couplings between the roughness of the surface and the fraction of species just from the perspective of terms in a gradient expansion. But what is their meaning? How would you go in an experiment and try to figure out what they are? One of the parameters that I had introduced was this dependence of the average growth velocity on slope. And if I were to think about a surface that is always growing normal to itself, bacteria that are always isotropically growing normal to themselves, it is easy to check through simple geometry that the growth in the vertical direction is related to the amount that you are growing in the normal direction through a term that in its expansion will generate a gradient of h squared, in which case this parameter lambda is none other than the growth velocity v0. But that's not always the case that you have isotropic growth. And indeed, in this model that I had introduced before, where bricks were added to a surface, because of the different anisotropies that are inherently present in the way that this growth rule is implemented. If I were to look at the growth velocity of this system as a function of its slope, it actually goes down. So whereas in this isotropic growth, the parameter lambda is positive and equal to V0, in this particular model, lambda can in fact be negative. So the presence of lambda is imposed by symmetry, but its sign and its value is dependent on the microscopic model in question. One of the other parameters that I had introduced here was what I call beta, and it describes the way that the equation for the fraction depends on the slope of the surface. And it kind of looks like a term that is advecting the fraction f with the velocity that is related to the slope. And indeed, the way to check the presence and the behavior of that term is to again grow a colony on a sloped front, but rather than looking at, say, the vertical velocity, one can look at the way that one of these sector boundaries is changing. And by looking at the way whether this sector boundary drifts down a slope or goes up the slope, one learns something about this parameter beta that we had introduced before. There were a bunch of other parameters. There was parameters that were like Laplacian of h times f, gradient of h squared f, which are like the parameter tau that was multiplying f. And the meaning of this parameter tau, like in the usual time-dependent Landau-Ginzburg equation, is whether the f equals to 0 state is growing or decaying. And so the transition point usually is that tau equals to 0. So tau equals to 0 for a flat surface would describe the extinction transition. And here, by looking at this, we can see that the location of the extinction transition could potentially be modified by the shape of the surface. Why should an object that is moving on a slope have the same extinction point as the flat surface? It does not necessarily have to have that. And by looking at the location of the extinction point, for example, one can determine these parameters.
May I ask a question?
The point is, yes, please, go ahead.
Yeah. This discrete model, is it same as the Eden model? Because it looks like the Eden model, right?
Yeah, so these are all variants of the Eden models, except that when you have two colors, you have to make a decision about not only adding a particle here, but also the color of that particle.
Okay.
So that gives you an additional degree of freedom. And indeed, in the simulations of this model, the difference that we has between the one that corresponds to the picture on the left and the one that corresponds to the picture of the right is when we are dealing with a sloped surface, the way that we choose in the color depends on the locations of the colored blocks that were before.
Okay.
So it's a variant of the Eden model where you can bias the color that you add depending on whether you are growing in a geometry like this or in a geometry that is sloped like this.
Okay.
And that degree of freedom allows you to have a microscopic model whose macroscopic consequence is different value of this parameter beta. Okay. Okay. So in principle, one can, through macroscopic observations, such as the dependence of velocity or drift velocity of the sector on slope, or the dependence of the extinction point on slope, determine these macroscopic parameters that I have indicated over here. But there's also consequence on the morphology. And so let me show that by focusing on several of the important parameters that determine the shape. I already discussed this parameter lambda, which is the dependence of the normal velocity on slope. I had introduced the parameter alpha, which determines whether one of the species grows in the vertical direction more than the other. So let's say in the pictures that I have over here, the gray species wants to grow in the vertical direction more than the blue species. And that is captured by this parameter alpha. And it is appearing here as something that prefers f equals to 0 or f equals to 1 as far as the growth velocity is concerned. Now, if one has both alpha and lambda present, then you can see that the shape of the growing front is very different, although in both cases, the gray is the species that wants to bulge out. If you are dealing with a situation where lambda is positive, the shape of the front is where the one that is growing faster is actually forming a flat facet, and the one that moves slower actually slopes, because a sloped surface grows more rapidly because of this lambda parameter, and thereby catches with the gray. Whereas if one is dealing with a lambda that is negative, it is the more rapidly growing one that becomes sloped, so that the velocity goes down and can be matched with this other one. So this is an example of how the combination of these parameters, G and alpha, determines the morphology of the shape. But we also have other parameters. And one of the other things to look at is what happens if in the pictures that I had over here, the fitness of the gray and blue was kind of similar, so that the boundary between them was more or less going up vertically. Whereas generally, one of the two species could be growing more rapidly in the horizontal direction, and then a number of morphologies emerge depending on whether it also grows more rapidly in the vertical direction or not. And some of these morphologies, again, depending on the shape of lambda, will be like bulging up in the shape of an inverted V, or bulging down in the shape of the V, or having circular fronts. So there's a whole bunch of things that one can imagine can take place. And actually, there is experimental example of that now. So this is an experiment that was done by Kirill Korolov in the lab of Jeff Gore only very recently, where they had a species that was colored red that was growing out on a film. But occasionally, this species could mutate and create this green species. Now, the green species was more fit, and you can see that the green species eventually will get rid of the red species. But during the process that it is growing out and competing with the red species, it is actually smaller in size, so that it does not bulge out, but has a depression in the front. And the shape of this depression is described by these kinds of V patterns that we had seen before. And so again, we can reproduce more or less all of these patterns that are seen in the experiment by running the kind of equations that I had mentioned before. So this is one aspect of the morphology that emerges by thinking about these competing species and how they grow. The other, but clearly in this part of the problem, I did not focus on the roughness, So these are things that emerge by just looking at the deterministic versions of these coupled equations. And one can sort of think about solving the deterministic equations just to get some shapes in more general circumstance. And I'm going to introduce this part of the discussion, which is actually the last part of the discussion, by looking at the generalization of what I had introduced before, in which I had different two species that were growing at different rates and mutating among each other. So let's imagine that I have a number of different species whose numbers alpha could be n1, n2, etc. There's a number of species. Their numbers, if there was nothing else, would grow exponentially at rates that is governed by these growth factors. One can have the possibility of mutations in which the different species mutate among each other. If they are present in space, they could diffuse in space. I will assume that all of the diffusion coefficients are the same for simplicity. These equations are all linear and are a version of something that is called Eigen's model of quasi-species. The populations of them would be governed by this linearized equations. But the advantage of linearized equations is that they are exactly solvable, and I can formally write the solution of these equations as a function of time through the exponentiation of this linear operator acting on the initial state of the population. While these equations are linear and exactly solvable, they are not a good description of a population because of the exponential growth. So the fate of the population is either exponential decay or exponential growth. Indeed, the average, not the average, but the total size of the all of the populations, if I were to add all of the species, grows with an average growth rate, which is obtained by multiplying the individual growth rates and the fractions of the various populations. The fractions, which is n alpha divided by the total n, themselves grow. The rate of growth of a fraction is determined by its individual growth rate minus the average population growth rate to the lowest order. Now note that since the average growth rate depends on the fractions, this is in fact a nonlinear form. G bar is a function of f, so the equation for the fraction, because of this term, is no longer a linear equation. So we started with a linear equation for the total number, the fractions become nonlinear. There is another place where this nonlinearity appears, in that the Laplacian term also gets a coupling between the gradient of the fraction and the gradient of the log of the total number that is growing according to this. So this is just sort of a simple manipulation of the equations that were linear. If we look at the fractions, they have these nonlinear forms. Now, this nonlinear form suggests a kind of similarity between the term that I had before, where there was a term that was gradient of f and a gradient of h, and suggests that maybe I can take advantage of that and have a mapping in which I think of this as some kind of a new height function related to the logarithm of the total number that I would have had for this linear set of equations. And in that case, I reproduce a version of the equation that I had before. That is, I would have, first of all, a height function that has this type of dependence on slope, and has a dependence on the various fractions. So this would be the generalization of the alpha f that I had before. And the different fractions essentially behave according to an equation that is kind of similar to what I had before for directed percolation, but there is now a coupling between the gradient of the fraction and the gradient of the height functions that I introduced. Now, clearly, not all of the different nonlinearities that I had introduced before is present in the equation that I generate from this linear form through this so-called Kohl-Hopf transformation, but it is kind of similar, and many of the features that I had in the previous equations could potentially be present in these equations. There is some other symmetries that emerge, like the parameter that indicates the gradient of h squared, and the parameter that is the multiplication of grad f grad h is the same one. It's the same lambda. And this is actually corresponds more to the isotropic limit that I had very briefly discussed previously. Now, while this is not the full set of equations that I had introduced before, it has the advantage that is exactly solvable, because these set of equations can now be mapped back into the original linear equation, and the original linear equation I can solve in general. And once I have solved the linear equations, I can take the logarithms and do fractions and have figure out what the growth of the different fractions is. So essentially, this is what I have written over here. Assuming that there are no mutations, then each one of the terms would grow according to a standard, using the standard diffusion kernel, starting with some initial condition that I impose, and then I can do the sum, and I can look at the fraction, etc. I'll just tell you what the answer is. And the best way to describe that particular answer is to show you a picture. So what is shown here in this picture is evolution of a profile of a species that were of two different colors, the blue and the gray. And the difference, rather than the original experiment where there was a flat initial condition because they put a knife edge that was flat, let's imagine that the initial knife that they put had a corrugated form and it was bent like this, and that somehow they managed to put the blue species in this version part of the initial corrugated knife edge, whereas the gray species was elsewhere. And then we allowed these species to grow. And this set of equations described how these profiles change as a function of time, and how the different fractions that exist at the front are whether coming from the initial gray or the initial blue. And we can see that, for example, in this case, the initial profile grows and gives you these kinds of hills which come together, and that the blue species has kind of grown on this particular hill. Now, what is interesting about this is that the set of parameters that are given to this evolution equation are such that the blue species is in fact less fit than the gray species. So that if I had started this thing on a straightened version of this profile, the blue species would have quickly gone extinct. But here I gave the blue species a geographic advantage because it was sitting on top of a hill. And while it was less fit than the gray species, because of its geometrical advantage, it was able to establish for itself a niche, and this niche exists and grows for a while. Ultimately, of course, the whole thing will become more and more flat, and when it becomes flat, the gray one would have the advantage and the blue would disappear. But just because of this geometric advantage, we can see that this blue species can live for a while and uh, essentially prosper. So there's some interesting features of these coupled equations that can emerge if the deterministic forms are, for example, solved not on a flat initial condition, but a more complicated initial condition. Okay, so let me summarize the various things that I have told you. So the problem of range expansion is when a new species is growing into new territory. And if that is the case, most of the activity and interesting things are taking place not on the population that is left behind, but on the front of the population that is advancing, because that's where the competition between the different subpopulation takes place. Now, generically, one expects this expansion front because of the fluctuations to not be something that is flat and boring, but should have some interesting fluctuations in shapes. And these fluctuations in shape and the corresponding roughness have influences that one can see, for example, in the more rapid disappearance of diversity and in the ability to find common ancestors very at earlier times. Now, if the species also compete with each other, not only in the sense of by fluctuations, but in the sense that one of them has some advantage over the other, either through appearance via mutation or because of the way that they're growing, then the situation becomes more complicated, and one can write down equations that govern the fraction of different species that are occurring at the front and how they are coupled with the shape and fluctuations of the front. And the simplest set of equations that one can write down is in a sense of a gradient expansion parameterized by just 4 coupling constants. One of them tells us whether which species tends to advance into the new territory more rapidly. That's the parameter alpha. And then there are other terms that describe how the fraction of the different species changes, how those changes are modified by the curvature and slope of the front. For example, modifying the way that the boundary between 2 sectors is advancing on a slope front, or how the extinction point depends on the curvature and slope of the front. Together, all of these things give rise to interesting profiles of these advancing interfaces if we forget about the small fluctuations and think about the overall shapes. And these shapes could have either these V-shaped character, or they can be circular in shape. And that depends on the combination of parameters that we had introduced before. And at least some of these shapes have already been observed in experiment, and it would be good to see whether other ones of them are also possibly present. And finally, that some version of the deterministic equations that has some underlying symmetries, but hopefully is sufficiently generic, can also be solved subject to any initial condition through this Kohl-Hopf transformation. And at least one interesting example that I can point to is a case where an unfit species, because of a geometric advantage, can persist and grow in a niche for a while. So this is work that was done in part with more senior collaborators, David Nelson and Daniel Beller, and a former graduate student, Sherry Chu, and postdoc Jordan Horowitz, who's currently faculty at University of Michigan, and the current graduate student, Daniel Schwartz. So I thank you for your attention, and I'm happy to answer any questions you may have.
Yeah, thank you very much. Yeah. So if there is any question, you can take. I have a question. This is there like a one-dimensional TASEP kind of particle model for this kind of problem? Like, I'm not sure whether this question makes sense also, but like, for example, if you did not have colors, then this the surface you get described by some kind of TASEP model, right?
Right, right.
Yeah,
It's an
but
interesting question. I guess you can maybe start thinking about a version of the TASEP models in which there are multiple colors,
yeah,
but that the colors can change to each other.
yeah.
So you can have, let's say, particles that are hopping in one dimension to the right or to the left that are also endowed with some color. And then you can have rules by which the jumps to the different sides can depend on color, as well as how the changes in color depend on either some mutation rates in which as you jump, you could change color, but also maybe depend on whether your neighbors are the same color. And then one color is when you have two colors, one of them wins with some rate or the other. So we have not done any of that. I would not be surprised if there's some version of that that's possible. So that's certainly a very good question and something to maybe pursue.
Ayan, you have a question? Deepak, you are mute, Deepak. Deepak, you are mute.
Okay, now I can. Okay, I
Yes,
have a
yes.
question.
Yes.
So, there were these models called crystal growth models in which you have two kinds of sodium potassium ions which grow into a common crystal, mixed crystal. They sound like this your stepping stone model with two colors.
Yes.
So what is the connection? Is this exact equivalence or somewhat related or what?
No, so those, yeah, so let's see. So we indeed looked at with Barbara Russell on versions of this. So let me maybe go to this set of equations. Okay, so from the perspective of continuum equations, I would say that the difference is that, let's say here, the underlying equation before coupling to the height model was the time-dependent Landau-Ginzburg equation. Okay, so, but then apart from that, if f was the order parameter, you would have said that essentially you get exactly the same type of couplings. The more important thing is that the noise term, the noise term here allows for f equals to 0 being an absorbing state. And so in the previous models, the crystal growth models, you had essentially, if you like, the deposition of both type of particles. So there was no corresponding absorbing states. Okay. So, but apart from that, it's kind of the same idea. So you take some underlying equation or some underlying model, and then add to it the possibility of the roughness in height, the fluctuations in height and how they get coupled to each other. So essentially, this version of the model stands to the version that you mentioned before, in the same proportion as, say, the directed percolation universality class to the standard Landau-Ginzburg.
Okay, thank you.
Ion, you can try now.
Audible?
Yes, yes.
Okay. So I had a question from this scaling form you showed towards the beginning of the talk. So,
Okay.
so I could not understand. So that kind of first passage thing was obtained from the I mean from the backward trajectory of the black trajectories, or the I mean forward trajectories of these colored lines, colored regions.
Right. So for the purposes of the simulation, we did it from the forward trajectory. That is, we started with some initial condition in which we had, let's say, one color, another color of a range delta X, and then back to the original color. And then we would run the dynamics of the model, which was, if you like, some version of the Eden model or whatever, for a while to see when the first coalescence was taking place. And then we would repeat that many, many times. So that's how we obtained the numerical results that went into constructing these figures. It is, so that's how we did it. We did not do the corresponding things for the backward curves, the ancestry curves. My guess would be that they are similar, but then you are saying that maybe because they start on a rough surface as opposed to a flat surface, there could be different. Yes, I cannot rule that out.
And also another thing is can you say what any thing about the microscopic dynamics of these black trajectories?
Yes, I can. Let's see, where do we want to go? I guess I want to go to the original thing. All right. Okay, so there is another version of the model that we simulated, which is the one that is shown here, which is somewhat different. So what we did was the following. We said that rather than growing asynchronously, let us grow them synchronously one layer at a time, but with the following modification. We say that the bacteria that we are adding don't all have the same size, but their size is taken from some distribution. So some of them could be smaller, some of them could be bigger. Now, when I want to add a new one and I have to choose between this neighbor and that one to grow, I decide based on how far they are already. So I look at the current height of the two, and then the new height I will take as the maximum of this height plus a random number, or this height plus a random number, where the random numbers are taken from the distribution of the sizes that I can add. Now, this becomes identical to the problem of finding a optimal directed path in a random medium. And so this is, if you like, a way of translating the directed paths in a random medium to the problem of a height that is growing. And these are the pictures that we generated through this other interpretation of the directed percolation universe from the directed polymer. And they are no different, essentially, from the ones that were generated through this process. So in that sense, there is a very close analogy between these coalescence paths and the directed paths in random media, if that's helpful.
Okay, thank you.
Yes, I have a question. So And in the second last slide, you had shown Eigen's model, right? So in that, could we calculate an alpha independently and then calculate f alpha f? Wouldn't that avoid the nonlinearity which would come in the equation?
From the eigen equation in the linear form, we can certainly calculate an alpha immediately. Yes. Except, so what was your question then?
So like when we write it in terms of f, we have a nonlinearity, right? So can't we get all the results without introducing that nonlinearity?
We can certainly solve these equations completely, but they don't correspond to any physical system because of the exponential growth.
Okay, so what is introduced in that equation with rate of change of f alpha? What more is introduced, which is not in
Okay.
Eigen's model?
Okay, so eigenmodel corresponds to a set of numbers that are growing in a space and exploding. Okay, so that's something. Now I take the solution to those equations that as such are unrealistic, and I map them to a different problem that may be realistic. And the way that I do that is I take the log of this exploding number, which is the total population, and I call it a height. Whereas this n was exploding exponentially, the height now grows grows linearly. And I regard it as the height of a surface that is going up. So some exponential growth in one perspective on the solution to these equations becomes the height of an interface. On top of that height, there are fractions. And because they are fractions, they are not growing to infinity. They are between 0 and 1. And those fractions are evolving according to this equation. So there are two different perspectives as solutions to a mathematical equation. So they are not exactly the same. This fraction does not describe these numbers in a realistic sense. It's a mathematical mapping. And the trick is an exponential growth has been reinterpreted as a height of something.
Yes, thank you.
Hi, thank you for this very inspiring talk. So I was wondering in this competitive reproduction mutation model, so with the nonlinear terms, so can we make any comments about the population statistics?
Can you say what you would mean about population statistics?
So for example, you have two species, right? NA and NB.
Yes.
So then there are certain rates at which they switch. And so we could, if the model is linear, you probably can solve them and say something about the population statistics. So now with these linear terms, nonlinear terms on them, so can we comment something about them?
So here, I guess I was, through this mapping, I'm looking at a deterministic version of the equations. There's certainly a stochastic version. I can add noise to these equations and have a noise acting on the fraction. And then rather than, even if I start with a flat surface, because of the fluctuations that are in the equation, there will be fluctuations in the numbers. I assume that there is some version of it that one can turn into some meaning of statistics. So, for example, if we were to look at a height of a growing surface, there is a description of the probability of that height in terms of a Tracy Widom distribution. It would be interesting to see whether there is an analog of that that tells you something about the probability distribution of the fractions that are varying stochastically, and whether there's some other universal distribution that characterizes that. So I think that's a very good question. I would like to see it better formulated in terms of exactly what question we want to ask about the statistics of the fraction. In the same sense that I have a precise question about the statistics of the height, to which there is this interesting answer that it's a Tracy Widom distribution. If you can formulate a question about these fluctuations of the fraction, then maybe there is a corresponding interesting distribution for that.
Thank you. Thank you very much.
I guess, yeah, we don't have any more questions. Yeah, thank you again for a very nice talk. Yeah.
My pleasure. Thank you for the invitation.